So we pulled the amplifier board out, the first one, and this is the one on the left, and this was the one that was giving us the little bit of DC offset drift. But we want to see if we can make it better now. And the first thing you would go for on these normally would be these little potentiometers. They're known to be troublemakers. Unfortunately, when I recapped this and everything, I realized that I did not have these two values. There's a 100 ohm and a 150K, I believe. So they're kind of odd values, and I thought I had them in stock, but I came to look and find out that I did not. So I had to order them, and I didn't want to hold up production, so we put it together so we could get some testing done. That being said, I am quite sure that the pots are not causing the DC offset drift. It's probably one of these components in here. I could sit here and monitor it for a long time, trace it to the individual component, but to what end? We're going to replace the components. And I did a very exhaustive search of what I want to do for this particular receiver, and I've kind of made up my mind. And the first thing I'm going to do is going to be a little bit unique. This is going to be a first for me, but I will tell you that I kind of give a little bit of credit to Chris Hoppe over at hoppesbrain.com. If you recall, I did a restoration of an ADCOM GFA 585. Check out that series if you get a chance. And one of the things that he did in his redesigned driver board was to be able to deal with these stabilizers. Now, what is a stabilizer or a stabilizer, however you want to say, or Pioneer calls them a varistor. Essentially, all this is several diodes wired in series and all put into one package. So this is going to have the equivalent of several diode drops, and there's different models, different versions. There's ones that will have 2 diode drops, ones that will have 3 diode drops, and even ones with 4 diode drops. And these are pretty much getting unobtainium to find. Now, the go-to fix for this over the years has been to get these. I'll show you. These are little 1N4148 diodes. And normally all you would do is just wire as many of these in series as you need to get the same diode drop as the stabilizer that you're trying to replace, and then you just kind of put them in here. And it works, but number one, 1N4148 is not a perfect replacement for these. You also have the messiness of seeing those cobbled together diodes. So I've always wanted to come up with something that would be better, you know. And lo and behold, Chris Hoppe used these. He found these and he integrated them into his upgrade board. And these are modern stabilizers. And you can see, if you get this particular model, CMX STB 400, and you can see they come from Mausers. I'll hold it still so you can look at the part number. And they come in these tiny, teeny little holders like this, and I'll show you one. They are really tiny. I mean, here's my fingernail, and look at these things in here, how small. So they're just absolutely tiny. But if I show you the data sheet here, the thing that I really like about them is when you look at the internal wiring diagram of the 400s, there's 3 models. There's one that has 2 diodes, one that has 3 diodes, and one that has 4 diodes. I just buy these because they'll take the place of these for what we're doing. And you can see, depending on which pins you connect to, it can control how many diode drops you have. And so it works perfectly. They're thermally coupled inside the package. They're very tiny. They look very neat. And I have seen a couple of things out there where people have tacked on wires to them and kind of put them in, but that's really very delicate. So I thought there has to be a better way. There just has to be. And sure enough, thanks to the magic of eBay, I found these little boards. And here, and please don't ask me where I got them from. It was just one of those on, China type things. These literally cost pennies for one of these. And there's 2, 4, 6, 8, 10. There's 10 boards all kind of together. So you get a package of 10. And literally this thing wasn't even $1. It was very cheap. And you can see their surface mount, and you can actually mount the chip on there and then use these little eyelets to wire it for whatever type of component you need. So if it's an SV03 or an SV04 or SV02, whatever the case may be, just connect the wires for whichever you need. And I'd made one up, and afterwards after really struggling here to see everything, this is what it looks like. So I just made up 8 of them, and then they just kind of break apart like that. And you can see that's what one looks like. So if we look at the size of this, compare it to the size of this, you can see they're almost the same size. So it'll work out extremely well, and they are an absolute perfect match for these SV series. Absolute perfect match. So that's what we're going to put in there. I'm going to get those installed first, and then we'll talk about the transistors. And I promise you, that's another thing, guys. I have been swamped with requests to talk about the output transistors on this. What I'm going to do is I did a complete scene on that, a complete clip on that in the AUX1 restoration video. So what I'm going to do is I'm going to take 2 of the tracks. It's about 4 minutes long, and I'm going to put them in this video, just kind of re-upload them into this video, and it'll explain to you the difference between like a ring emitter transistor versus an LAPT, large area parallel transistor type transistor, and it'll give you a little bit of idea of how they build these things to have such a high transition frequency in a power transistor. So I promise I'll put that in there somewhere. Anyway, let's get these mounted in and see what they look like, and then we'll start working on the transistors. So I've pulled the first one out, and there it is. And if we connect it to the original stabilizer that we pulled out, and yeah, if I'm not saying stabilizer the way you say it, tough. I'm not an English major. So you see we have about 2.54 volts, 2.53, somewhere around there. And we take our new one. So if we connect this up like this, we turn it on. At 2 mA, you're getting a drop of 2.62 volts. At 5 mA, it's 2.8. At 10 mA, it's 2.98. 15 mA, it's 3.08. And back to 2. And you can see that your voltage drop changes with current. Okay, so you can kind of plot a little curve based on that, and then you can take your other device that you want to compare it to. For instance, let's take one of these and make sure I clip it in there the right way. And if you turn it on, 2.54, and you're going to see this is close but not perfect. At 5 mA, 2.67, 2.8, 2.79, 2.86. Okay, so it's going to change, and if you, even within the same ones, they're not all identical. That's one of the problems I'm finding with these older ones that you pull off these boards. They can vary pretty greatly because they're old, whereas those ones that the new ones, they're all very, very almost identical to one another. The quality control on those things is amazing. So this one's about the same, 2.68, 2.79, 2.86. So this one's pretty close to the other one. Chances are these ones are probably still good. I don't know. I mean, they usually hold up pretty well. Rarely do I have them be bad, but I have had the ones on the boards be bad. Usually these ones here, if they're bad, as the temperature goes up on the transistors and the amplifier warms up, you'll see that the bias it'll drift all over the place. If you turn the amp off and it cools back down and then you turn it on and the bias is perfect again, most likely one of these is going to be your problem, because this is right in line with that bias circuit. I'll show you again. You can see right here, these STV2H and STV4H, that's D5 and D7. So there's D7, there's D5. These two in the middle, those are the two that are connected to the heat sinks with the white wires on them. So these would be D5 and D7 here, this one and this one attached to this heat sink. And notice they're attached to the heat sink because they're designed to change their value. So this bias spreader will actually change the bias as the temperature heats up, and it's supposed to do that. It tracks thermally, and that's what holds the thing in bias. This is your bias pot right here. So when the amp, basically you want to turn it on, wait. I usually wait a few minutes to stabilize. I'll set it with this, and then what I do is you notice I was checking the temperatures of the heat sinks, and then I would go back and check my bias voltages after that. And as long as it was holding, at idle, then we know these components are good. These ones out here sometimes will get a little bit wonky on the board, and I don't know why. You would think they would be the more stable ones, but I've seen them go bad a few times. That's why I'm replacing them. But again, as we talked about earlier in this video, if this changes, that crossover point where these things are turned on will change, and you'll either get crossover distortion or the amp will have high bias and it'll run hot when it doesn't need to be. So that's why those are important. But we're going to leave these two alone because, again, these were tracking, but the offset was drifting. That's why I think it's probably either this transistor here or this guy up here starting to go. But we're going to replace everything on here. I'm getting ready to replace the transistors in this thing, and the question I get more often than I care to think about is, how do you choose substitute transistors? And I am personally, this is a personal opinion, I am adamantly against just going on Google searching and finding some link to some article on some website where somebody lists a list of transistors replacements. Now, while that can be very good and that information can be very useful and very accurate at some times, a lot of the times I find that there's stuff that's not entirely the right thing. You can't trust everything on the internet. And although it's extra effort to go through the motions and to learn, how to do this, I find quite often that it is really worth it. So we're going to go through how I do it. And by no means, number one, you're on the internet right now and you're looking at someone on the internet. So by no means am I saying this is the only way to do something, nor am I saying is this the only transistors that will work. I'm just kind of showing you how I go through the motions of researching things like this. So let's start with this, and we're going to start at the very beginning and kind of work our way through. Now we're going to start at the very beginning here. I got a comment the other day from a viewer, and he was asking about some of the big transistors you see sometimes in phono stages. And of course, phono stages are notoriously low power, right? A preamp is very low power. And he said, why do you need big power transistors? Well, the reason that you see things like that is the further you get to the front of an amplifier, the more gain they put. In other words, if you start at the very beginning of an amplifier, even before this, clear back to the phono stage, through the flat amp, through the tone amp, all that, into this part of the power amplifier, all the way to the outputs, you'll find that as you go closer to the output section, the amplifier will have less and less gain in each stage. So most of your voltage gain, in other words, we want the amplitude of the signal to increase, but not necessarily the power or the current of the signal. In the very beginning, all we want to do is take that teeny little voltage and increase its amplitude to have a higher amplitude to work with the power section. So keep that in mind as we go through with this. So at the very beginning here, we have this little stage, and this is kind of like your pre-driver or your preamp stage. And this is where most of this entire amplifier's voltage gain or amplitude gain is going to take place. So it's going to take a relatively small amplitude signal, where it's on pin 4 here, where it says in, and it's going to run it through this little stage right here, and we'll talk about it in a second. And then it is going to pass it on, and of course you have your bias spreader, and then you have your pre-drivers and drivers, and finally out to your outputs. And this is a very unique little circuit, and what we call this is a differential amplifier, but it's more than just a plain differential amplifier. So if you just see these two transistors at the top, the way they're configured, the reason it's called differential is this particular circuit is designed to work in differential mode. In other words, the greater the difference between these two terminals, the base of these two transistors, the greater the amplitude output will be at the emitter collector junction, right? So the reason that we do that is to get a lot of gain, but also to reduce noise. We'll talk about that here in a second. Okay, I'm back. Even though I am past working hours today, when you own a business, sometimes you gotta take calls, and today has been a really wild, crazy day, so you'll probably see the video cut in and out, in and out, and in and out throughout this whole part, so I apologize in advance. Anyway, if you see, this is a differential circuit, and then you have this cascade under here, and what its purpose to do, here we go again, sorry. So normally you'd see like resistors right here, but if you notice, you have these two transistors, which are, resistors are passive components. In other words, they never change their values, whereas these transistors are active components, and they'll change value as the circuit works. So what you're essentially doing here is you're lowering the impedance while still maintaining the gain of the circuit. And that's very important, because as we lower the impedance in here, you're actually lowering the possibility of noise. So not only does this give us the gain we need, but it also does it with low noise. And this also has a very high common mode rejection, which is going to also get rid of noise. Now, if you look at these two little innocent looking resistors here, they go all the way back to the output section. So your output transistors are going to be connected way over here, and it comes back and through here, and it goes through like this little divider network, and this actually is your negative feedback. So remember, we talked about this is a differential amplifier, and if this were just a fixed value normally, which would be like you'd have a reference voltage set there, and then by changing the signal here, putting your signal in here, that would make a big change up here. That's your amplification. Well, by adding this negative feedback that's out of phase, it's actually going to be actively reducing the gain somewhat. It's also going to greatly reduce the distortion. So this is a really good circuit, because you have high gain, low noise, and you're reducing distortion globally throughout the whole circuit. Down here at the bottom is a current mirror. This is what this is called. It's a current source is really what it is, but the circuit itself is called a current mirror. And really what this is going to do is this is going to make sure, this is going to always keep this thing up in push-pull stage. In other words, it's not going to allow the thing to turn off. And by having this by raising this up and putting in a constant current source, this also is going to increase the gain. It's going to it'll probably about double it, and it will also prevent any kind of even ordered harmonics getting in here. So this is, and you can read about this. There's a lot of books that talks about this. Let me think offhand, one good one. The Art of Electronics is one, and actually I have a copy of that here that I can show you, that I keep right by my desk. So it's by Paul Horowitz, and it is called The Art of Electronics. And let's see if we can look this up in here. Let me see if we could look up a current mirror. So I'm going to try to keep this camera between me and the book. But you can see there's a whole section on here. It's actually very good. And one of the things is current mirrors can be used in transistor circuits wherever a current source is needed. They're very popular in integrated circuits and in these old circuits, which kind of mimic what a op-amp circuit does, where a matched transistors abound, and the designer tries to make circuits that will work over a large range of supply voltages. And it goes on and talks about the different types and how they work. But of all the books out there, Art of Electronics is one of the best. Now I had several when I was in college. I had some books that were exceptional, but they were a lot more specific to different parts of electronics. But if you just want the overall just basics of electronics, kind of a reference type book, great book. I highly recommend it. Anyway, how do I get off topic all the time like that, huh? So anyway, what we have here is a circuit that gives us high gain, low noise, reduced distortion, minimizes the even ordered harmonics, everything all in one little circuit. It's a neat little circuit here, the way they did this. And this is pretty common. Different variances with or without different components of this circuit, you will see time and time and time and time again in many different amplifiers from this era. Now, with the advent of integrated circuits and op-amps and things like that, these kinds of things started to go away, which is why you don't see them as much anymore. But if you're going to build a discrete component amplifier, this is a great circuit. Now, as I said, I'm going to say this again and again in this portion. Anytime there's a difference between these two elements, these two bases, you get a big difference in here. So think about this for a minute. What happens if one of these transistors is different from the other? In other words, if one has a different gain characteristic than the other, or one has a different VBE, which is going to really affect it big time, because your voltage drop here is going to affect all of this down here. What's going to happen? It's going to make this thing operate non-symmetrically. So that's why having matched transistors up here is so important. Now, as we get down here, they should be matched, but they're not. It's not quite as critical that they're perfectly matched as these top ones up here, the actual differential pair itself. So that's why you see that transistor that we looked at before that looks like this. And this is actually a 2SA, right here is a 798. What we have here is a 2SA 979, but they're similar. You have two transistors in one package. Now, why would you do something like that? Well, first of all, the transistors in here are perfectly matched. They are identical copies of one another. And on top of that, they are as close together as possible, so they're both going to be subject to the same temperature and signal variances, outside interference together. And they're both going to thermally track with one another. So if one of them warms up, the other one warms up with it. And since transistors can change in a predictable way with current, it'll ensure that these always stay matched. Now you could replace this with two discrete transistors. And I have the amplifier here. And you could see that little transistor down there if it'll focus. There's your 2SA979. You can actually put some of these amplifiers, not this one, but for instance, I think the SX-1980, for instance, it actually has extra holes drilled in there that you can either use one of these all-in-one packages, dual transistor packages, or two separate transistors. But if you use the two separate transistors, you either have to make sure they're very close together, or even you put some epoxy between them, or some thermal. I have actually thermal epoxy that I use that thermally couples them. And that's probably what we're going to do here when we replace this. These transistors can be high failure items. They're right at the front end where all the signal comes into the amplifier. They have the most gain, so any little change to this with age, any little noise that it develops in one of the transistors in there is going to really affect the sound down the road for the amplifier. So we're probably going to make a differential pair, or our own matched pair of transistors. And I'll get into that here later on. You've seen me do it before, but a lot of you seem to be new to my channel here and haven't gone back and looked through some of my other videos. And I can appreciate that, because I didn't do a very good job of cataloging what I did in each video. I show that it's an amplifier that I restored, but little techniques that I teach are different for every project I do, and I do that on purpose. But I should have done a better job of documenting it. Anyway, so then we have this little transistor here that looks very innocent. And this is actually an input transistor that can absorb the base current of Q2 up here. It actually will absorb the base current up here. And it'll hold the voltage at a set resistance. And this is basically where you're going to set your DC offset. This is actually tied down here to your DC offset pot. And if this little transistor gets kind of drifty and changes, gets old and starts to drift with age, you can see it's directly in line with that pot. And what's going to happen is you're going to swing one side, either more positive or more negative, and you'll still have your AC swing from there, but the actual offset is going to be not at 0 volts. And that will carry all the way across here, all the way to your outputs, and you'll have DC on your outputs, because this is a directly coupled amplifier. So a little slight change here with that offset pot will make a big change at the outputs. So this one would be another candidate that why we would want to replace this, because we're getting some offset drift. Remember, we're doing all this because the left channel had just a tiny little bit of offset drift. And like I said, it's not the potentiometer. Although the pot is hard to adjust because it's a single turn instead of a multi-turn pot, it is working very well. And if you don't move it, it shouldn't change, and it's not changing, but the voltage is changing. So one of these active components is starting to get a little bit flaky with age. So we're going to replace all these. And then if we move down here, you have your bias spreader. And these two transistors here are for your push-pull pair. See, this is where you're actually seeing your push-pull. And the amount of voltage that these are set to, okay, is determined by these diodes. These diodes each have a drop across them. See, like this little diode package has 4 little diodes in one package. That's what we were replacing there on the board. Okay, and the thing is, how many diode drops and how many volts you set these at is how far apart the upper and lower, the NPN versus the PNP side, the complementary pairs are going to, it's going to adjust that overlap. The idea is, when we talk about, see, one thing leads to another, doesn't it? Whenever we talk about a class AB push-pull amplifier, you can never let the transistor turn completely off. So if both transistors are turned completely off at the same time, there's going to be a little gap from when both transistors turn off till one of them picks up and turns on. So in other words, down the road here, like in these drivers, before this one, when this one shuts off, this one is not on yet, and then all of a sudden this one goes off, this one turns on, and your signal swings from positive, then goes off, then there's a delay, then negative. Well, you don't want that. If you have a delay from when you change from positive to negative, what's going to happen is that the transistors are going to have a dead zone, and that dead zone is called crossover distortion. I'm sure a lot of you who are into this have heard of that. And so what we want to do is we want to turn these transistors on in such a way that they never shut completely off and that they even overlap one another slightly, so that before this guy turns all the way off, this guy's already picking up the signal and turning on, or picking up the signal, I should say. It's already partially turned on. It has to be turned on past its VBE. So in other words, if your voltage drop across, base emitter is 0.6 volts, 600 millivolts, then you never want to let this transistor have less than 600 millivolts across here, or what's going to happen is transistor's going to turn off. That's what this little circuit here does. It ensures that they're always separated so that they're both turned on slightly. And then this pot right here is going to adjust how far turned on they are. If you turn them on further than you need, you really won't notice anything. You'll still hear the sound. It'll sound good on the amplifier. If you turn them off too far, you'll get that crossover distortion. But if you turn them on too far, all you're doing is you're generating excess heat, because by turning them on too far, you're causing the output transistors to dissipate that energy that they're not using. And all that's going to do is heat up the amplifier unnecessarily. So the name of the game is to adjust this whole mess here until the transistors are turned on enough that you don't have crossover distortion, and no more. And that's a very slight amount, and it's not going to cause any heat. It's going to allow the thing to idle very, very cool. So if you ever had an amp that you turn it on, and after about 5 minutes, even if you're not listening to music, if it's all the volume's all the way down, you notice the heat sinks are getting warm already, it's because the bias is set too high. You can turn that down a little bit, and you still won't get the crossover distortion, but you'll notice the heat sinks will cool off. That's what this is doing. So the further across we get here, the less important it is that these are matched pairs, because really at the end of the day, no matter what's happening difference between all of these, by the time you get to the output section, this DC offset adjustment is going to compensate for any differences between the pairs, and it's going to actually bring everything to the center. But this part here, not so much. It has to stay very matched. So we're always going to use matched transistors here, and then I like to use matched here and here simply because it's going to make it operate a little more in the center of where it was designed to be. Even though if they were a little bit mismatched, you probably wouldn't notice anything. Up here you would. So that's our first thing. Now that we know all that, let's talk about the transistors as a device in and of themselves, and how we're going to determine what we're going to replace them with. So we have a little bit of advantage because we have a full service manual which gives us a parts list. Now if we didn't have a parts list, the first thing I would do is I would go to the actual circuit board itself. I would look at the components themselves, and I would write down each and every component that's in there, and maybe even how many of each, but at least all the different ones that are on there, I would list them. Luckily, we have that here, so we have a list. Now, this is the first place to start with this. Sometimes you will get an actual part number. Sometimes you'll get a manufacturer's part number. Like if you try to look at some of the Macintosh amplifiers, they have Macintosh part numbers, and unless you have one of their charts that converts that to an actual, Motorola or some other, actual part number, it's hard to tell what they are. That can be a little more challenging, and that's probably another video there. But for right now, we have a list. So we're going to write those down. And what I've done is I just took Notepad on the computer and I made a list. And after I made the list, right next to it, I made a substitute that after I chose it, I wrote it down. But the first thing I did was I made the list, and then I looked each one of these up and looked at just a couple of the basic characteristics of the transistors. Now, there are ways to do that, and I'll show you. So, of course, the first thing you could do would be to go onto the internet and do a Google search, and a lot of times you can find a lot of these things. You can find places that have data sheets, and there's lots of them, and I'm not even going to name them, but if some of you wish to share some of the ones you use, go right ahead. But there's many, even places like Mouser and DigiKey, for their particular products, they have data sheets attached in their website for each product that they sell. Another thing I like to use is a little app called NTE Quick Cross, and this is not the end all. If you use this, it will show you an NTE equivalent that supposedly will work, but I will guarantee you it's not always going to be an identical match, and it's also going to depend upon the application of that transistor, how good their substitution will work. So just you've been forewarned. But you can use this here, and for instance, we can type in something like 2SC-1775, and it says it's transfers to an NTE 123AP, which is a very, very generic transistor. That's one of the ones that a lot of the small NPN transistors will cross over to, and obviously that one transistor can't be identical to every transistor that's out there. What they're saying is in many applications, or most applications, it will work, but there's times that it won't. So I like to use some alternative methods. Number one is the online, like I said, like the Datasheet Archives or somebody like that. There's lots of them out there. But you really can't beat books. I'm a book guy. I like to have my books. I've had them for years and years. And you can see a lot of these. You can actually look up the transistor, 2SC-2938, and it gives you some basic attributes, and it even has a couple suggestions for substitutes and even what the transistor looks like. So this is a good book right here. Let me back the camera up a little further. It's trying to make it easier for me to stay near the bench and still be behind the camera, but I got to give you more range here. So here's one right here. And this one's a good one, and I think this one is still, you can still get this one, and let me give you the ISBN number. There it is. I think this book is still available. The next one that's not available, I don't think, but they're out there, is the Transistor Substitution Handbook by Sams. And there's all your, and see, these were only $4.50. You know, when I was a kid, this stuff was cheap. You could get these books everywhere. And now they're starting to get pretty expensive to buy online. But you can see it's page after page after page of transistors and some different substitutes that they use. Here's another Sam's manual. Okay, and I have bunches of these books. I just took a couple off the shelf here. And you can see, once again, it gives you some basic parameters of the transistor, and really depending on what part the transistor plays in the circuit is going to depend on which ones of these are the most important. But I'll give you a clue. Your breakdown voltages and total power dissipation is important. In amplifiers, your transition frequency is going to be a big deal, but depends again on the amp. You know, like that AUX1 and this amp, transition frequency is extremely important, and you're going to find out when you look at the what I found on these ones. Every single one of these have triple digit transition frequencies in the megahertz. This is megahertz, so this has a transition frequency of 200 megahertz. What is transition frequency? Well, that's another whole lesson in and of itself, and I'm not going to get into it today, but it is the frequency at which the gain of the transistor becomes unity. In other words, at some point in time, the transistor no longer has the ability to produce gain, forward current gain, beta. When beta becomes 1, this is the frequency at which that happens. So that kind of gives you an idea, and it's really giving you a factor of what kind of slew rate or how fast that transistor can turn on and turn off. It doesn't necessarily mean what frequency you can operate the transistor at. We're more concerned about how fast that transistor can turn on and turn off. Okay, so again, you can see that Pioneer chose all high frequency transistors for this, for the same reasons that Sansui did on that AUX1 video that I did. So if we look at these characteristics, then we can go and actually go through some of our standard transistors that are available out there. And these are the ones I chose. And the reason I chose them is, for instance, when you look at this 2SC1775 and you look at the voltages, you look at the collector current, you look at the maximum power dissipation is about 300 milliwatts. You look at the beta, this is a high gain transistor. It's actually a high gain low noise transistor. It has very high transition frequency. If we pull up the data sheet on a KSC-1845, which I should have brought a printout of that and I didn't. Maybe I'll put it up on the screen if I remember here when I'm editing the video. These come in different varieties. So there's a KSC-1845 and there's up to four or five different ranges of gain, of forward current gain. If you use the one that's in the F or the E gain range, it's going to be very similar to this transistor. And all of the properties of this, including the VCEO, which that's an important one, collector emitter voltage breakdown. This one's rated at maximum 90 volts. I think this one's good for, 120 volts, so it well exceeds that. The power dissipation of the transistor is 300 milliwatts. But in this one, I think these ones are good for 500 milliwatts. So this has all the characteristics of this transistor and can actually exceed them a little bit. So this is a good substitution. And this is how I went through and did all this. And if you look down here, for instance, if you're ever looking at a 2SA733 to replace, this is kind of an oddball one. And you can actually... The BC556 turns out to be a really good replacement, but if you go in and look at the KSA992, which is kind of the complement to this KSC1845, it will work, but I believe this has a higher total wattage. It's a 500 milliwatt transistor, but it has a lower, I believe, collector current. It can only dissipate 50 milliamps of collector current instead of 100 milliamps, but it is a much higher voltage. It's double the voltage. It's 120 volts. So as long as you don't have high collector current in that circuit, this would be a suitable replacement. You see how I'm saying you kind of have to know what you're looking for. So in this instance, if this, I don't have any of these BC556s in stock. I'm going to have to order them. But I do have KSA 992s, and we can look at the schematic, and if we can determine that there's going to be less than 50 milliamps of collector current, then this would be a suitable replacement. So that's how you do it. Now, how did I come up with this from this? Okay, well, you kind of have to know what transistors you have available. Now, I did this based on what I have in stock. I have a large part stock of spare parts, and all of these were ones that I, with the exception of this BC556, these were all ones that I had. But this one had that problem, which is why I started digging through some of the other transistors out there. And this is one instance where I went online and I did some Google searching, and I found a couple people that had used these in, had recommended using these in other, not necessarily in this amp, but in other amplifiers, by typing in 2SA733 substitute and Google searching that. But I didn't just believe it when I saw it. I then went and I got a data sheet for the BC556, and I looked it up, and then I compared it, and I found that the BC556 is by far the best substitute. And by the way, while I was looking, I also noticed that other people had chosen the KSA 992, but they never mentioned about the difference in the collector current. So that was one of those things, if I'd have just listened to it, this may not have worked. So again, do your homework, do your research when you do this. So I hope some of those things make sense. I know, a lot of you are going to say this is long-winded and takes too long, because if you're experienced with electronics, it's boring for you. You know all this already. Those of you who are learning are going to come away and say, man, you didn't cover enough. And I agree. There's a lot more that you could talk about with this, but I just have limited time that we can talk about this. So ask me questions. That's what the comments section is for. And I may not answer them right away if I'm not at the computer, because I'm very busy, but when I do have the time, I will answer you. And if you email me, you have a much better chance that I'll answer you. I usually do emails once every 2 weeks. So usually the longest you'll wait for an answer from me is 2 to 2.5 weeks or so, and I'll get back to you. If you catch me at the right time, you might get a quick answer if you're close to my schedule. So anyway, there we go. Just so you know, I also looked up the couple of diodes that were on there and found out that these would be good replacements. The 1N914 is one that I have in stock, so that's why I kind of looked it up, and here it turned out to be a perfect match for these 1S5555/1S2473s. It depends on, Pioneer used these two components interchangeably, and they're both listed in the parts list that you could see either one in that position. They both cross over pretty well to this. And same thing with this one, this 1S1886. It's just a standard 600 volt 1 amp general purpose diode, not high speed or anything. And I have 1N4007s and UF4007s, which these are just a little faster recovery version of these. So they're both the same other than that. So I can use one of those, and which is what I'll do. But now that I have my list, it's pretty easy. I just go to my parts stock and I'll pull these out. And wherever I see one of these, on this side, I'll replace it with one of these on this side. All right, we're going handheld here, and we're at the curve tracer, but we're not going to use this to match these transistors, but I want to show you something, how important some of this is. So remember how I told you that we are going to use a KSA 992, a pair of them, for the to take the place of that 2SA 979, that dual package? Well, you're now looking at the curve for a KSA 992, and I have two of them in here, and actually we can compare two of them. So we have one in here, and they're both KSA 992s, If I go to the other one, so we're going to switch over to this one, take a look. What happened to our curves? If I put it on compare, you can see the two sets of curves, and you can see this set here, there's much higher gain. So is there that much inconsistency with these transistors? Well, no, it's kind of a trick here. Let's take a look at it. So if you look very carefully there, you can see that they're both 2SA992s, but if you look, there's additional little numbers at the bottom. And one of them says, what does it say? I can hardly read it. One says FCE, and the other one says, what does it say? Hold on. I can't see through the camera. FBCF. So those letters are very important. Even though they're both 2SA992s, they're different gains. And you can buy the same transistor in different gains. In the old days, you would just buy a transistor, and then you would have to kind of match them. You'd just go through a bin of them and kind of match them up. But they're already binned for you when you buy these. As long as you get the correct gain value, which is determined by that little letter after the part number, it will get you very close to a match set, even without matching them. Now, I would not recommend that, but if you don't have a means to match transistors, and I'm going to show you a very easy, inexpensive way, but if you don't have one, you can always, if you buy them that way, you can be assured that they're going to be pretty close right out of the box. So now let's look at the way that I actually match transistors for this particular circuit. Now this does not work. You need the curve tracer for anything that's going to have any high power on it or any high voltage on it. But for what we're interested in on this, we're really interested in using them in a differential pair. And we want to see what happens when they turn on and off. We're going to use this little method that I've been using for about a year or two now, and it has worked out really well, so I'm going to share it with you now. And I did a video on it earlier, but it wasn't perfected. Now that I've been doing this for about a year or more, I'll show you what we're doing. Alright, so what I have here is a little gizmo that I use to match transistors, and it is a kind of a variant of the basic VBE comparator, and which is kind of like based on the Wheatstone bridge. We talked about that in the first video where I was kind of figuring this all out, and I screwed up on the diodes and a couple things. And it's still posted. I didn't take it down, so you could see all my mistakes. There they are. Anyway, so this is different from that though, and what I'll do is I'll post several images on the screen as we're talking here on and off, and you can pause the video if you want and kind of check them out with a schematic and some screenshots of what this thing looks like and some instructions of how to use it. But I'll go over it with you real quick. So basically there's a ZIF zero insert force socket that I put on here, and there's a little, it's just a divider circuit, and we have a transformer here that's putting an AC signal, and this one just happens to be putting plus 25 volts center tapped onto this circuit. And I have two of the KSA992s in here right now, and we're going to take a look at them on the scope. Now, little disclaimer, you can use a digital scope on this and it will work just fine, but some of the details probably won't show up. And it's not about the, again, as I said earlier in this video, it's not about the megahertz of your scope. It's really about the sample rate and how it samples the image and displays it. Noise is very hard to display on a digital scope. It's very easy to display on an analog scope. So we're going to use this on our old Tektronix 2465. But even like a little Tektronix, even my LBO 505 leader scope, which is just a 5 megahertz analog scope, works perfectly. It's not about the megahertz. Anyway, let's look up at the scope and see what this is doing right now. And again, I'm going to post some of the images here up on the screen too. So there's a big fuzzy mess on the screen, right? See it? And what you're seeing right here is the difference in VBE between the two transistors. So you see right here is your zero line. The transistors are turned off here, and the transistors are turned on here. And if you kind of look at the schematic, we're actually putting an AC signal on there. So for half of the waveform, the transistors are going to turn on, and for the other half, they're going to turn off. And we're going to talk a little bit about that in a minute here. But as you can see, this fuzz right here, this is your VBE. If they were perfectly matched, this would, in theory, be dead center. It's never going to be perfect, but you would see this would look like one fuzzy straight line. Now, as you can see, we're at minimum. We're at 2 millivolts per division, because really the difference in VBE is very slight on these transistors, but these ones are not matched. I'll tell you that right now. And we're going to go up now in voltage. Wrong way, if I turn this thing the right way. And if you look right here, see these two little points here? Look, this one is only going about 1, 2.5 divisions, but this one's going 1, 2, 3, 4 divisions. It's actually going off the screen. So these 2 points are very different. And what you're looking at is you're looking at the transition of the transistors turning off and back on, kind of against one another. And what's happening is if these 2 transistors have exactly the same slew rate and exactly the same gain and exactly the same VBE, these turn-ons and turn-offs should look exactly the same. They should be symmetrical, but they're not. So you can see these transistors are not matched. And the reason they're not matched is I actually have the one type of KSA-992 and the other type of the KSA-992 in there. The two that, as you saw on the curve tracer, were different, had the different gains. So let's now put, I'm going to unplug this for a second, and that's just garbage you're looking at right now because the scopes, everything's unplugged. Let me put the correct transistors in here. Just hold on for a minute. And let me turn the camera off so I don't waste film here, or data space, whatever you call it today. Okay, let's plug it in. And as you can see, it's changed now, isn't it? And they're a lot closer now. This one's going 1, 2, and just a little over 3. This one's 1, 2.5, just about. So they're much closer. And when we go down to our 2 millivolts, you can see how this one, it actually starts in the center here now. It does kind of drift up a little bit, so one transistor does have a little bit different slew rate than the other, but not much. This is a lot closer match. And if I go and put another pair in there, we can keep going until we find a set that are closer. Give me a second. And here we go. 1.5, 1, and just about a half. Almost perfect on there. And still gonna have pretty close there too. See, almost all the way across now, it's perfectly matched. Okay. Now, let's talk about something else. What happens if I heat one transistor up? So I'm going to take my fingers like this, and I'm just going to put my finger on the one body of the transistor, kind of like this. And watch what happens to those lines. You see the one on the right? What happened to it? Went way up, right? So let me blow on it. And you can see it'll start to come down as we cool it off. See, it's slowly coming down. There it goes. See it? Now we can see the tip of it right there. And if I keep going, it'll pretty much line up with this one. Now watch when I grab the other transistor. What happened? The line on the left goes up. So what this is kind of showing is it's kind of showing the thermal response of these transistors. And it also shows that when we get them down to same temperature by blowing air on them, that they'll actually come to an equilibrium where they're pretty well matched. See, I'm kind of just fanning them with my hand right now. Now, sometimes you will see a little notch like this, and that's normal. Again, I've seen that. It doesn't seem to affect the transistors at all, how they match. It's just a characteristic of when the transistors are starting, one's turning off and one's turning on. So there you go. Or not one turning on and one turning off, but as they both turn on and both turn off at different rates. That's what I'm trying to say. In a perfect world, these little tips would be really small, and they would be perfectly symmetrical, and they would be almost perfectly, like, no distance between here. So I've done this basically with 2 resistors, a 10-turn potentiometer, and a transformer, and some, mechanical parts like a connector and, so forth. But it is about the most inexpensive tool you can build. And I'll tell you, using this to match small signal transistors gives you a lot of information. Now, you can kind of do this if you put the curve tracer in compare mode and so forth. And again, with the curve tracer, you can plot all kinds of different curves, for collector emitter current, VBE, gain, all those things you can look at. But it's pretty extensive, and a curve tracer is a lot of money and a big pain in the butt to set up all the knobs for each different type of transistor. And I guess if you use them a lot, you can get pretty quick at it. But this is for small transistors, this is the way that I go now. I don't even use the curve tracer on those anymore. The problem with the little all-in-ones, like these little things here, they don't necessarily put different signals and things, and they only check at like one setting. The more expensive version of this, which I have here, is a little bit of a gimmick if you ask me. This one, I never ever use it. It has a USB interface, and it will quote unquote plot the curves. But if you look at the current differences for each curve, they're so close to one another and they're so low power that it's really kind of insignificant. So and again, if you ever tried to plot curves with this, it's really slow. So again, this little device that I use seems to work really well, and it's fast. You just can swap out transistors like nothing, and it's very easy. Now watch what happens if I put a different PNP that's not even the same brand of transistor. So I now have another PNP transistor in there right now, and it is not a KSA at all. And if you look, let's go up a little bit on the intensity. If you look, first of all, you're actually getting a little overshoot on this side. You can see they're grossly different. I mean, like big time. And if we go down to look at the VBE, It's way down here. And again, we want it to be close to the middle, or at least we want most of it to be in the middle. So this is a very unmatched pair of PNP transistors. And this just goes to show the difference when you have two different transistors with different transition frequencies, different gains, different things like that. They don't work correctly when you're putting them in a pair together. So there you go. We're off the charts there, and like I said, a little bit overshoot here. And if we put the right one back in, and this is another one. This is another of the KSA 992s, and I've been holding it in my fingers while I was putting in there, so you could see it's a little bit hot right now. And if we just kind of give it some time to stabilize, let's see how close this one matches. Again, this is the correct type out of the same bin. So see, I'm fanning it right now. I'm fanning both of them together is what I'm doing, because they're right next to one another. And looks like they're getting pretty close to one another. And go down to our 2, and you could see that's a nice matched pair there. Look at that. All this noise is right in the middle. Now once again, if you're looking at this on a digital scope, you're going to see a bunch of dots, and it's going to be hard to read this. So you really kind of need an old cheap scope. See that? This isn't necessarily a cheap scope, but it's an old scope. But even just a normal analog, even 10 megahertz, 20 megahertz scope will do this perfectly. So I hope you enjoyed that. I'm going to match these transistors. I'm going to get them put together, and then we're going to make up our little packages and get them installed. The next version we're going to talk about is what we have up here. And remember when I told you that I wasn't sure if these Sanken transistors were ring emitters or not? I thought they might be, but they weren't. It turns out they are not. They are actually LAPT process, which stands for, and I highlighted it for y'all. I printed this. This is straight from Sanken's website, okay? You can look it up. You can go to their website. They have so much information on the process, how they produce transistors and so forth. And it stands for Large Area Parallel Transistor, okay? And essentially what that means is, as I told you earlier here in the video, it's very easy to make a small, low power, small signal transistor have a very high transition frequency. So the idea with this was, why can't we just take a whole bunch of those and parallel them onto a die so that you have the high transition frequency, but you have the higher current capability of a power transistor, because all these transistors work in parallel. So these are LAPT type transistors here, okay, these Sankens, and that's what they're using in the AUX1. And again, these ones can work up to 40 megahertz, but even higher, these ones up here even work into the 60 megahertz range, which is pretty good. So that's why if you were to take a standard power transistor and put them in place of these, or you were to take a lower frequency driver or preamp transistor and put it in place of one of these, the amp would lose all of its magic. Because what would happen is it would defeat the purpose of what they were trying to accomplish. Now the other thing that doing this does is it allows the amplifier to be designed to have a lot less negative feedback. So when you look at the amount of negative feedback in this amplifier, it is lower than the amount of negative feedback you would see in a standard design of amplifier. So there again, by not having the proper amount of feedback and not having the proper frequency transistors, this amp actually won't sound very good. So it's an all or nothing thing with this amplifier. Again, I could put MJ 21193 and 21194s in there, and it would work perfectly. The amp would come on, you would be able to play music, and it would not go into parasitic oscillation nearly as easily. So it would make the amplifier more stable. However, that sound, that very clear open sound stage that this thing is known for, and you have to hear it to understand what it is, would be gone. So again, this is an all or nothing amplifier. It's useless if you put the wrong silicon in here, which is why Sansui went through all this trouble to design this amplifier around these transistors. Unfortunately, in my opinion, they failed at doing that. I think that this thing was rushed to market, and later versions apparently dealt with it better and were more reliable. And there are modifications that can be made to this amp to make it reliable, so you don't have to worry about it. But bottom line is, when it's working, the sound is amazing on these, from what I understand. I've never heard a properly working one ever, so this will be a first for me. I can't wait to hear it. But also, we have to make sure that we don't allow those situations where this thing can go into oscillation. And part of it is all those little bypass capacitors. They're designed to snub out the ultra high frequencies, but still allow enough of the transients through that you don't get that TIM distortion. And it's a delicate balance. That's why if you notice, some of those caps we were changing in there were 1 picofarad. And even increasing that to 2 picofarad would change the sound of this amplifier. Even though those little capacitors are not directly in the audio path, they can actually attenuate the audio path if they're the wrong value. And conversely, if the value drops because the capacitors go bad or wear out or fail, all of a sudden the amplifier is highly susceptible to, you guessed it, parasitic oscillation. So it's a delicate balance. So that's why I used very high quality ceramic NP0 capacitors that were very small surface area, but still had a high enough 200 voltage rating. And hopefully between that, careful cable placement, wire placement, and everything, we will be able to get this to be a perfectly working amplifier and have that sound that we're looking for. So this was a long-winded talk about transistors. Some of you are probably bored to tears by now, and some of you hopefully, answered some of your questions, because it's a big topic to talk about, and it probably requires somebody smarter than me to really explain it well so that it's understandable. But anyway, that's what we're talking about with these transistors. That's the difference between a standard bipolar transistor, a ring emitter transistor, and an LAPT processed transistor. And I hope you understand what TIM distortion is, what this amplifier does to deal with it, and how these transistors were made. That's really all I'm trying to get through this video. So again, I thank you all for listening, and I thank you guys big time for catching me on that. I did not catch those 2 driver transistors. I did not catch that they were only 4 megahertz transistors. That would have kind of defeated all the purpose, and I probably would have been all patting myself on the back how good I did, because it doesn't go into oscillation, when probably it may have been, who knows, I may not have even fixed anything, but by putting those transistors in, who knows. So anyway, thank you again. I hope this was a little bit informative and cleared the air with some of this, how this works. And I'll be coming back very soon with the next part in this series. Thank you guys, and take care. Be well. Bye-bye. So the first thing we're going to look at is the ring emitter type transistor. So as you remember from looking at this one, those are called the straight finger junctions. And as you notice, they look like this. And of course, what do you have when you have junctions? You have capacitance. Okay, so what we want to do is we want to kind of reduce that area. So they worked with some different things. The first one they came up with was a horseshoe type junction. And you have your P and N junctions situated around. So this center part is your emitter, I believe. Or is it your collector? Or no, maybe the base. I don't know, guys. Help me out. Anyway, the contact area is here and here and here. And if you notice, you have a different amount of area the way this is situated. And what it does is, being in this ring, semi-ring area, they call this a horseshoe, it actually reduces that capacitance and increases the transition frequency of the device, even on a large device. You can actually cut this die thinner so that it will have lower capacitance because of the way this thing's designed in a ring area. Now the next version is called a Pac-Man, and you see what they did here is they actually, this center area is now completely encapsulated, and then the other junction is doped on this way here, but you still have an opening here. And then finally they came to the process called a true ring emitter, and that is where the emitter is a complete circle around the base, just like that. Okay, so this was a majorly improved version of power transistor, allowing you to have high frequency and allowing you to have be able to use that high frequency to minimize your TIM distortion, or your transient intermodulation distortion.